Hello again. This is our video solution to problem 10 from Superquiz 3, and we're on to spherical coordinates. So here we're trying to show that the volume of the upper half of a sphere centered at the origin with radius 10 is equal to 2,000 thirds times pi. So we know that we can compute the volume of a region by computing the triple integral of the constant function 1. So if I want the volume, this is going to equal the triple integral over the region. So E is going to be what says here, the upper half. So we can draw a nice sphere. This will be the upper half of the sphere. The radius here is 10. And this is your E. So we're going to integrate over E, but then we just use the constant function 1, and that will give us the volume. Now, in order to compute this triple integral, we're going to have to write down E, and of course we want to do it in spherical coordinates. So let's try that. So E in spherical coordinates, so we're going to have a rho, a theta, and a phi. Again, the theta and the phi, we're referring to the mathematical notions there, where the theta is representing the radial angle and phi is representing the co-latitude, or the sometimes called the azimuthal angle. Anyhow, what do we know about our rho? Well, we're inside a sphere of radius 10, so rho will go between 0 and 10. How about the theta? Well, down in the xy plane, we get to go all the way around, so theta will go between 0 and 2 pi. And then phi, again, that's representing this co-latitude, right? So your phi is the angle that you make with the ray heading towards the North Pole and whatever point you have on the sphere. And so that can go from 0 down to pi over 2. So phi will go between 0 and pi over 2. All right, so we're going to be able to rewrite our triple integral in spherical coordinates as an iterated integral. Rho can go from 0 to 10. Theta goes from 0 to 2 pi. Phi is going to go from 0 to pi over 2. We have the constant function 1, so we don't have to evaluate that anywhere. But when we convert dv into spherical coordinates, we get the Jacobian, or what I call the cost of doing business, and it's a rho squared sine of phi. Okay, well, I guess I'll stick to the same phi I've been using. Okay, and then we have d phi, d theta, d rho. All right, well, let's see. Why don't we get this description of E out of the way. Move that down a little bit. And now we can go through, and we notice here that all of these are multiplied together, and the rhos and the phis and the thetas are not intertwined. So actually I can break this up into 3 different integrals. So first I'll have an integral of rho squared. Then I'll have, well, this is really great. There's no thetas in here at all. And then we'll have the phi integral, and that'll have a sine of phi. All right, so this first one I'll actually compute out. So we get rho cubed over 3. Rho goes from 0 to 10. The second one is quite easy because it's a constant function 1. So we're just asking what's the length of the interval. Of course, that's 2 pi. And the third one is this common integral that we've done again and again, where you ask what's the area under the sine curve between 0 and pi over 2, and the answer to that is 1. All right, so in total, let's see, when rho is 0, nothing will happen. At 10, we're going to get 1,000 over 3. Then we multiply by 2 pi times 1, which is 2 pi. And so in total, we get 2,000 thirds times pi. Hey, that's what we were supposed to get.